Good evening everyone. Welcome to Gate Academy Global. So tell me whether it is visible and audible or not. Is it everything clear to you? Yes, good evening Dolly, good evening Mohammed, Shivani, Shiva, Ashish, Rohan, Amit, Govind, all of you, good evening. Yes, everything is fine. And am I audible? Yes, Rick, good evening. So how are you doing? Nazia, yes, everything is clear. So our today's topic is delta modulation and the differential pulse code modulation, right? So today we are going to discuss about the differential pulse code modulation. Okay. So our next topic is differential pulse code modulation. So tell me, it is visible or not? Is it visible? Yes. Okay. So in the differential pulse code modulation, what we do, actually what is the basic principle behind the differential pulse code modulation? Why do we apply the differential pulse code modulation technique? Even we are having the pulse code modulation technique, but still we are applying the differential pulse code modulation technique. So what is the reason behind that? So suppose we use the non-return zero signal. We saw that the bandwidth is what? RB, and when it is returned to zero signal, bandwidth is what? 2RB. Okay, and when there is a Nyquist pulse, then bandwidth is RB by 2, which is minimum bandwidth. Okay, so that is the minimum bandwidth. So in all the case, the bandwidth is directly proportional to the bit rate. Okay, in all the case, bandwidth is directly proportional to the bit rate. And what is the value of RB? So it doesn't depend on the type of encoding scheme. The bit rate doesn't depend on type of encoding scheme. So RB is always equal to NFS. In case of pulse code modulation, RB is always equal to NFS. Now we can say that this bandwidth is actually proportional to the number of bits. Here also the bandwidth is proportional to the number of bits, and here also we are having the number of bits. So the bandwidth is proportional to number of bits. Okay. So if we want to increase the bandwidth, or if we want to reduce the quantization noise power, to improve the SQNR, the quantization noise power is given by delta square by 12, and actually it is nothing but the VH minus VL whole square divided by 12 into L square. So in this way we say that the quantization noise power is inversely proportional to 2 to the power 2n, isn't it? So what will happen if we increase the number of bit? What will happen? What will happen if we increase the number of bit? Good evening, Nilanjana. Yes, so from this particular discussion, we are saying that if we increase the number of bit, the quantization noise power reduces, and if we increase the number of bit, the bandwidth increases. Okay, in all the case. Yes. So we are saying that if we increase the number of bits, the quantization noise power reduces and the bandwidth increases. So but we never want to have a large bandwidth, because to transmit a signal we always want to have a less bandwidth. We want the channel bandwidth to be large and the signal bandwidth to be less, because if the signal bandwidth is less, more number of signals can be transmitted using that large bandwidth of the channel. Is it okay? So we always want to have the large spectrum. So the large spectrum, if we are having the large spectrum, we can transmit more number of message signals if the message signal bandwidth is less. So if you increase the number of bit, the representation of the signal bandwidth increases. Devendra, communication crash course will be taken by Neeraj sir in Hindi in the Gate Academy channel. Okay, so that will be taken by Neeraj sir, and that will start from 10th of October, and the announcement will be done tomorrow at 5 p.m. Yes, so I am saying that if number of bits increases, the bandwidth for the signal which is to be transmitted gets increases, and if it is increases, we cannot transmit more number of bits at a time from the channel bandwidth. So we don't increase the number of bits beyond certain limit. Okay, we don't increase the number of bits to represent the each sample beyond a certain limit. So what will we do if we want to increase the signal to quantization noise ratio? If number of bit increases, signal to quantization noise ratio reduces, that is okay, but we cannot increase the number of bit after certain limit, beyond certain limit. So we have to fix the number of bits. So if we fix the number of bits, the quantization noise power can be reduced only by reducing VH minus VL. Can only be reduced by reducing VH minus VL. Is it clear? Nazia, it is up to you, because I have already covered the communication crash course from the scratch, that is from the amplitude modulation and the angle modulation, random variable, random process, and if you are having ample amount of time to study the same thing again and again, then you can study from the Hindi also, that is from the Neeraj sir. You can take. For those students who have not attended the class from the beginning, for them it is okay, but if you have already attended the class up to this point, that is the baseband transmission, so there is no need of attending the same thing again and again, because we are having the 3 to 4 months only. So it is up to you that how to utilize your time. If you want to read the same thing, then you can watch those videos also. Okay, Nadia? Bit duration is inverse of bit rate. If you want to calculate the bit duration is the inverse of bit rate. Okay, so I was telling that if you increase the number of bit, what will happen? The quantization noise power reduces. So we have fixed the number of bits. So if we fix the number of bits, the quantization noise power can only be reduced, because when we fix the number of bit, when n is constant, n is fixed or n is constant, L is also constant. Okay, because n is 2 to the power n is equal to L. So if n is fixed, the number of level is fixed. So if this VL is fixed, this L is fixed, then only this term VH minus VL will remain, which can reduce the quantization noise power. So to reduce the quantization noise power, to improve the signal to quantization noise ratio, we have to reduce this numerator. So how can we reduce this numerator? That is the concept behind the differential pulse code modulation. So the differential pulse code modulation gives an idea that how you can reduce the VH minus VL. Okay. Now, is it clear up to this point what we want? Okay, what is the purpose? What is the aim? Is it clear to everyone? Yes. Okay, good. So we are actually transmitting the speech signal using pulse code modulation. This pulse code modulation technique nowadays it is used especially for the speech signal, that is our voice. So this voice is encoded using the pulse code modulation and then transmitted. So this voice signal or the speech signal are highly correlated to each other. It means that its value doesn't change very much frequently. Okay, the meaning of the highly correlated is that the value of the speech signal does not change very frequently, and our speech signal is having the maximum bandwidth of 3400 Hertz. So to sample that 3400 Hertz, we use 8 kilohertz sampling frequency. So let's discuss this thing. We are having the speech signal in practice. So this speech signal is having the maximum frequency, which is 3.4 kilohertz. Okay, so it is 3.4 kilohertz. So according to the Nyquist criteria, it should be equal to 2 FM. So it should have the 6.8 kilohertz, but this require a ideal low pass filter. So according to the sampling theorem, we know that the sampling frequency should always be greater than 2 FM in practice. So we select Fs is equal to 8 kilohertz. Okay. So is it clear up to this point? So to sample this signal 3.4, we use the sampling frequency 8 kilohertz. Now, if you are using the 8 kilohertz sampling frequency, the bit duration, or the not bit duration, sampling interval, this is sampling interval, sampling interval is 1 upon Fs, which is 125 microsecond. So actually it requires 125 microsecond to sample the speech signal. Now, if there is an autocorrelation function of speech signal, suppose this is the autocorrelation function of a speech signal. Suppose this is the autocorrelation function of speech signal. So this speech signal, the autocorrelation tells us that the speech signal is highly correlated. How we can say that? At tau equal to 0, we will get its maximum value, say 5. We are assuming that value and we are assuming the autocorrelation. The autocorrelation of speech signal has been found that it is having the shape like this because that is highly correlated, it doesn't change very frequently. Okay. Nutan, the 8 kilohertz is practical value that I am assuming here, that sampling frequency for the speech signal is, in practice it is taken as 8 kilohertz. Now I am saying that at tau is equal to 0 the value is 5 volts suppose, and according to the sampling theorem the samples are taken after 8 kilohertz, or you can say the samples are taken at the interval of 125 microsecond. So when will I select the next sample? So we will take the next sample after 125 microsecond. So suppose here it is 125 microsecond, and after 125 microsecond we have found that the value doesn't change very much. Okay, so after 125 microsecond we found that the value, that is the amplitude, is only 4.8. okay. So the differential pulse code modulation says that instead of transmitting the sample itself, in the present case, in this particular case, whenever we get the sample value we quantize that value and then after encoding we transmit the signal. Here we are saying that don't transmit the sample value itself, take the difference between the two successive samples. So if you take the sample between these two samples, that is one sample which is having the 4.8 value, first sample is having the 5 volt value, if you take the difference, between the samples, it is only 5 minus 4.8 which is 0.2. So it means now you have to quantize the signal which is having the amplitude 0.2. okay. So previously when we have not discovered this differential pulse code modulation technique, whatever sample we get, whatever the amplitude of the signal we get, we quantized and then transmit it through the some coding technique, that is pulse code modulation. But if we transmit the difference between two successive samples, we get the very less value because it is the nature of the speech signal which provides very high correlation between the samples. So we are having very high correlation. The high correlation means it doesn't change very fast. The value of the amplitude goes slowly. Okay, so it decreases slowly. So that is why we can use this particular coding technique to reduce this VH minus VL, that is the dynamic range or peak to peak value of the signal or the amplitude of the signal. So instead of transmitting the sample itself, if we transmit the difference between the two successive samples, the step size get reduced for a given L. Okay, if the L is fixed, you can reduce the quantization noise power by reducing the numerator value, and this numerator value can be reduced by taking the difference between the two successive samples. So that is the principle behind the differential pulse code modulation. So is it clear up to this point? Yes, step size decreases but not, yes, step size decreases, but for a given quantization levels. So the number of quantization level was fixed. If you decided the number of quantization levels, say 16, 256 or something, so that number of quantization level will be fixed. The only change is in the value of amplitude of the signal, which is VH minus VL. Yes. So this is the principle, and the block diagram of this differential pulse code modulation we can see. And always remember that this is just because of the autocorrelation of the speech signal is very high. That is why we can take the advantage. Now, suppose as we said that the difference between the two successive samples is very less. Now, suppose if you are spending a time with someone for a long year, okay, suppose you are having one friend and you are spending the time with him for a long year. So did you yes, if you are spending a time with a friend for a long year, so can you guess his nature? Can you tell about his reaction at certain situation? So tell me this, if you are spending a time with someone for a long year, then can you predict or can you tell his or her reaction for certain situation? Will you able to do so? Yes. Yes. So why you are able to predict? Why you are able to predict? Because you are having the past values which you have seen at that situation. You are having some past values. According to that, you can predict that what he or she is going to do in that particular situation. Okay, because when we spend time for a long time with a friend for a long time, then we know that in certain situation how he or she reacts. He might aggressive, he might be cool in that situation. Okay, so in that particular situation we can guess. So that is just because we have seen doing so in the past. So we are having the past values of that person. That is why we are able to predict, or we are able to tell that what or he or she is going to do in that situation. So can you relate this? Yes. Now, if you are having the past values of the speech signal, past samples of the speech signals, then you will also be able to tell that what sample is about to come. Okay, if you are having the past samples of the speech signal, it has been found that if you are having the past samples, you will be able to predict the coming samples, because you know the past behavior. So you will be able to predict the upcoming samples or the present sample. Now suppose at tau is equal to 125 microsecond, I guessed that the sample should be 4.75, because I knew the past value, and because of the past value I am predicting that after 125 microsecond the value of the sample should be 4.75. Okay, but when I took the sample at 125 microsecond, I found that the sample is 4.8 volt. So what will happen? Now tell me what will happen. Okay, have you got this point? I had the past sample values, and according to that past sample values, I predicted that after 125 microsecond the sample should be 4.75. but when I took the sample, I got the sample value as 4.8 volt, then what will happen? Now again I am telling, the predicted sample according to me from the past value, predicted sample was 4.75 and actual sample when I took, okay, so the actual sample after 125 microsecond, the sample is 4.80. Okay, so if we take the difference between these two, what will happen? If we take the difference between these two, then what will happen? We get 0.05, only 0.05, isn't it? Okay, so when we took the difference between two successive samples, difference between two successive samples, we got the value 5 and at tau equal to 0 and at tau equal to 125 microsecond, we got that value 4.8. And the difference between these two is 0.2. So which one is better? Now tell me, in these two methods, which one is better? Which one will give you less quantization error? This one, right? First one. Yes, this one will be better because the amplitude difference is even less than this value. Previously, when we took the difference between two successive samples, we got the 0.2 volt. That is good. That is even better than the actual pulse code modulation. In actual pulse code modulation, the amplitude is 5 and then 4.8. But when we took the difference between two successive samples, the difference is coming as 0.2, which is better than the pulse code modulation. But we can even improve that system. We can even improve the system when we take the difference between the present sample and the predicted sample. So this is the present sample and this is the predicted sample. So I was thinking that at tau equal to 125 microsecond, the sample would be 4.75, but when I took the sample, I got the value 4.80. Now I am saying that if we take the difference between these two samples, then the difference is even less. So if the difference is less, the step size is even less, and if the step size gets reduced, then the quantization noise power will be reduced for a given quantization level. Is it clear? Yes, good evening, Vamsi. So I think now you have understood the actual principle of the differential pulse code modulation. So the differential pulse code modulation is predicted sample and the actual sample. It is the difference between the predicted sample and the actual sample. But it started from this particular discussion. It started from this particular discussion, and after that we improvised that system, and how to improve that system after taking the difference between the actual sample and the predicted sample. Yes, we are only focusing on the step size because we have fixed the number of quantization level, because to increase the number of quantization level we have to increase the number of bits, and if you increase the number of bit your bandwidth also increases. So that is why we are not increasing the number of bits or quantization level, we have kept that value constant and we try to reduce the step size by reducing the peak value of the signal. So we can reduce the peak value of the signal by taking the difference between the samples. So this is the block diagram of the transmitter of the differential pulse code modulation. So this is the message signal MT, or actually this is MK and this is M cap QK. So we will take the difference between these two. So this is plus and minus because we want to take the difference. So this is plus and this is minus, and here it is the difference signal. So this is DK and this difference signal is quantized. So we will get the quantized version of the differential signal, quantized version of the difference signal, and this difference signal and the predictor output, which is M cap QK, gets added and we will get the quantized version of the message signal here, and after encoding we get the differential pulse code modulated signal, DPCM. So this is the block diagram. So as you can see that we have already sampled the message signal. Okay, so I have written K here, so the K is integer. So I have already sampled the message signal MT. The message signal was continuous time continuous amplitude signal, that is MT, and that MT has been sampled in the sampler. So before this point the sampler was kept. So after sampling we get the sampled value or the discrete time signal. So this is the discrete time signal, and this signal and this signal we are taking the difference between the two signals. So when these two signals are taken as a difference we get this DK. DK is the difference signal, and when we quantize any signal we use subscript Q. So we are getting the DQK, which is the quantized version of the difference signal, and this difference signal is after encoding. Encoding means you can use non-return zero, you can use return zero, you can use Nyquist criteria. Okay, so after using any one of these three you will transmit your actual signal via channel, and that dqk is also given to this adder. This is the adder. You are adding these two signals. We are not taking the difference. We are only adding these two signals here, and it is given into the predictor input, and this is input to the predictor. Okay, so this is input to the predictor. Now what we will get if we write, and here I am saying that this is the quantized value of the message signal. So it is quantized value of message signal. Okay, so why we are saying so? Why we are saying this is the quantized version of the message signal? Even we are giving the message signal here, and we are giving the input to the quantizer, which is the difference between the two signal, but the message signal, quantized version of the message signal, we are getting at this point. Why we are saying so? Let me explain. So in this particular diagram, what is the difference dk signal? So this difference signal is m of k minus m cap q k, okay, which is the difference between the samples. Now whenever we quantize the signal, we get quantization error. Whenever we quantize, we will have quantization error, because quantization means approximation. So whenever you quantize any signal, you will definitely get some error. So that error is given by difference between input and output. So the difference is dk and dqk. We know that the quantization error is nothing but difference between input and output, and input is dk and output is dqk, so the quantization error is q. Now we can also write this dqk is equal to dk minus quantization error. Okay. Now we are saying that this mqk from the diagram is summation of dqk plus m cap qk. Okay, so we are having these two equations, first equation and the second equation, and now we are saying that after this adder we are having these two signals which is going to be input to the adder. So it will be mqk will be the addition of these two signals. So we are adding these two signals. Now what is the value of dqk? So from equation number 2 we can substitute the value of dqk. So this is dqk minus q, and we can also substitute the value of m cap qk from equation number 1. So it is mk minus dk. So if you observe this, you will find that this dk and this dk will get cancelled, and when these two dk will get cancelled, what you will get? You will get mk minus q. Now what this equation shows? What this equation shows? This quantization error, a quantized version of the message signal is nothing but message signal minus quantizer error. So quantization error is actually, what is the quantization error? So the quantization error is the difference between input and output. So input and output to the quantizer. So what is input to the quantizer? According to this equation, the input to the quantizer is mk. When you keep q here, so this from here you can write this q is equal to mk minus mqk. So mk minus mk is nothing but the input message signal and MQK is the quantizer output. So quantization error, it means that the difference between input and output. So that is why we can say that the quantized version of the message signal we are getting here, because here whatever signal we are getting, if I don't represent it by MQK, I will represent by some other variable like X, Y, Z, anything. But what I am looking after calculation, that this output of the adder is actually the message signal and the quantization error, the difference between the message signal and the quantization error. You can see here, this is message signal and the quantization error. So the difference between the message signal and quantization error is the quantizer output. So we are getting the quantizer output because this is nothing but the MK minus MQK. So both are having the same meaning. So that is why we are saying that even we are giving the message signal at the input of this adder, but the message signal, here we are quantizing the difference signal, but the message signal is quantized at this point. So we will get the quantized version of message signal at this point, even we are giving the message signal at this point. We generally know that if you give the quantizer input as a message signal, you will get output of the quantizer as the quantized signal. But in this particular diagram, it is not the case, because in the quantizer input we are giving the difference between the signal, and when you give the difference between the signal, so you will get the quantized version of the difference between the signal, but actual message signal quantized version you will get at this point. So this is just the basic explanation of this block diagram. The principle we have already discussed. Is it clear or not? This is just the mathematical form of the block diagram. Okay, just the mathematical form of the block diagram. The basic principle we have already understood. And Nandita, if we take the difference value, how step size will reduce? The amplitude already reduced. When you take the difference between the sample values like 5 and 4.8, if you use the VH as 5 volt, you will get the step size 5 square divided by number of levels, or 12. Okay, but if you use the 0.2, so the square of 0.2 will give you 0.04, so the step size gets reduced. Okay, Nandita, is it clear? So in this diagram we have this particular feedback path. This particular feedback path is itself a receiver, means the receiver is designed by the feedback path of the transmitter. This is the transmitter block diagram, and we are saying that the receiver is designed with the help of feedback path of the transmitter. How? So let's draw the receiver block diagram. Error we cannot remove, that quantization error will always be present and it doesn't matter. Quantization error is not a big issue. So the receiver block diagram. what I said, if you are transmitting the encoder, so you will get the decoder here. This is the decoder, this is input, and it is the channel. Okay, so after decoder you will be having adder and you will be having the predictor. The predictor output is m cap qk and the input to this adder is dqk. When we add these two signals we get mqk, and after getting this mqk, here we use the filter, reconstruction filter, and we get the message signal. I hope you will be able to see. So this is the DPCM signal, and this DPCM signal is transmitted. So once we transmit the DPCM signal, we will because at the transmitter we have encoded it, so at the receiver we will decode it, and once you decode the signal you will get this signal dqk. And now I said that this feedback path is nothing but a receiver, so this dqk will go into the input of the summer. So it is going into the input of the summer. The other input of the summer is m cap qk, which is the output of the predictor. So the predictor we have to place, and the output of the predictor is going into the input of the adder. So when we add these two, we will get the quantized message signal. This m cap q is nothing but a quantized message signal, and this quantized message signal will be passed through reconstruction filter. RC is reconstruction filter, and that reconstruction filter and the low pass filter both are same. So after passing that quantized signal through a low pass filter, we will get our message signal back. Is it clear? Thank you, Twinkle. So this is the differential pulse code modulation, and we have got the how to use that transmitter and the receiver block diagram, and what is the actual principle behind the differential pulse code modulation. Okay, so the bandwidth will remain same. Bandwidth we are not changing. Okay, so next topic is delta modulation. Delta modulation we are discussing. This is our last topic or second last topic of the chapter. Kritika, how many lectures are left? I don't know, because we have to cover 3 more chapters. So it may take 1 week or more than 1 week. I don't know, because I am not moving very fast. Okay, so here we are having the message signal, and when we take the difference between the two signals, it is important to make you understand. So that is why I am not moving fast in the digital communication. So in delta modulation, we use 1-bit quantizer. And here it is the sampling switch. And the output of this sampling switch is given as input to the integrator by feedback path. This is the feedback path, and after integration we will give again it into the input of the adder. Okay, so does anybody know what is the principle behind delta modulation? Can anybody tell this? Yes. No video solution because the faculties are not free, so we are not able to solve that test series questions in the form of video because all are doing other work. So this time we are not providing the video solutions. So next time we will definitely provide, but not in this year. Can anybody tell what is the principle behind this? What is the principle of delta modulation? Bandwidth reduced in this, but how? Okay, very nice try, Nutan. Your answer is correct, but what is the principle and what is the meaning of 1-bit quantizer? Okay, so tell me what is the meaning of, yes, Twinkle, used for transmission of voice signal, that is also correct. That is the application of this. I am asking the principle of this, principle of delta modulation. So anyone can tell this, what is the meaning of 1-bit quantizer? N is equal to 1, okay, fine. So if it is n equal to 1 means how many levels should be there? Yes, Manish, there are only 2 levels to represent the signal. There will be only 2 levels, number of sample reduced, 2 levels, yes. So now I am making this diagram also. This is the input output characteristics. Okay, so this is the input output characteristics of the 1-bit quantizer. This 1-bit quantizer will give you only 2 levels, and these levels are minus delta and plus delta. This is 0. Okay. Yes, 1-bit quantizer, 2 levels, as only 2 levels used. Okay, so this part is clear to everyone. What is the meaning of this 1-bit quantizer? So what will be the output of this 1-bit quantizer, whether it is a plus delta or minus delta. Okay, so it depends on the input, right? So we are saying that, okay, so tell me what is this, what this characteristics tells, what this characteristic tell. What will be the output of the 1-bit quantizer? Tell me what will be the output of quantizer. What will be the output of 1-bit quantizer? Signum function is the characteristics of 1-bit quantizer. Yes, Nadita, it works as a comparator. Very good. It is a plus delta or negative delta. Very good, Saeed. Plus delta or minus delta. Yes. So when you will get plus delta and when you will get minus delta? Okay, so let me explain you. Input is greater than 0, then plus delta, and when the input is less than 0, then minus delta. Plus delta or minus delta depends on the sampling switch. No, Akansha, it is a characteristic of signum function. Repeat a question, sir. Okay, Saeed. Okay, MT is greater than MQ2. Very good, Govind. Yes. So now let me tell you the detailed explanation of this block diagram of the delta modulation. Now here the difference is greater than 0 if MT is greater than MQT. Okay, the difference will be greater than 0 if MT is greater than MQT, and when the DT is equal to 0, output of the quantizer is plus delta. Okay, and if the DT is less than 0, if DT will be less than 0 if MT is less than MQT and the output of the quantizer is minus delta. The output of quantizer is minus delta. Is it okay? So yes, so if we take the difference between the two signals, we will get the difference signal, and according to the characteristics of this 1-bit quantizer, it says that when input is greater than 0, because this is the 0 one, input is greater than 0 means positive value. If the input is greater than 0, that means if input is positive, then the output is plus delta. That is difference. Input to the quantizer here is difference. So if the difference is positive, then the output is plus delta, and when the difference dt is negative, the output is minus delta. So when the difference dt is greater than 0, output is plus delta, and when the input difference is less than 0, output is minus delta. So this point is clear to everyone, I think. Okay. Now I was asking you what is the principle behind the delta modulation and why we are able to use this 1-bit quantizer. what we discussed in the differential pulse code modulation. In the differential pulse code modulation, the speech signal is having the autocorrelation function like this. At tau is equal to 0, we took the sample, we got the 5 volt. At tau is equal to 125 microsecond, we took the sample, we got 4.8 volt. That is okay, right? That is perfectly fine. Now, if you increase the sampling frequency, by 4 to 5 times of the Nyquist rate, what will happen? The sampling frequency previously we used is 8 kilohertz. That was greater than 2 FM. For speech signal, for speech. Now we are saying that if the sampling frequency is increased by 4 to 5 times of Nyquist rate, that means the sampling frequency is suppose 5 times of the Nyquist rate, so it is 10 times of the message signal frequency, that means it is 34 kilohertz. Is it clear or not? Tell me. Okay. This is for the DPCM. For DPCM, for speech signal, we selected the sampling frequency 8 kilohertz, which was greater than 2 FM. Then it was working very good, very fine. The differential pulse code modulation was very nice compared to the pulse code modulation, because it reduces the step size, hence reduces the quantization noise power, hence improves the signal to quantization noise ratio. But if the sampling frequency increased by 4 to 5 times of the Nyquist rate means 2 times FM, so we have increased the sampling frequency by 5 times of the Nyquist rate, we got this 34 kilohertz as the sampling frequency. So previously we were using only 8 kilohertz, now this time you are having 34 kilohertz. So for the 34 kilohertz, what will be the sampling rate? What will be the sampling interval? Tell me, what will be the sampling interval? Can anybody tell in microsecond? 1 upon 34 kilohertz in microsecond. What will be the value? In microsecond we are getting 0.09, as Suyash is telling, 0.09 microsecond. Okay, in microsecond somebody is saying 29.4. okay, so 29.4, I am not sure what is the answer, right? So 29.4 in microsecond, yes, yes, 29.4. 29.4, that means from the differential pulse code modulation you are taking the samples very fast. Is it correct? What does it mean? The sampling interval gets reduces. In the case of differential pulse code modulation, the sampling interval was 125 microsecond. The sampling interval was 125 microsecond, but in the delta modulation you are taking the samples in 29.4 microseconds, suppose 30 microseconds. So you are taking the samples in every 30 microsecond. So what does it mean? You are taking the samples faster than the differential pulse code modulation. So if you take the samples very frequently, very fastly, that means previously in 125 microsecond you were taking, then we were getting 4.8. Now if you will take the sample in 30 microsecond, which is approximately 29.4, so what value you should get? It might be 4.95 something. It might be 4.95 something, because you are taking the samples very fastly and you know the behavior of the speech signal. The speech signal doesn't change very fastly, and you are taking the samples very fastly. That means the sample you will get will have very less value, a very less difference from the previous value. Is it clear? Yes, Nutan, Nandita, Manish. Now it is very much close. Previously we were taking the sample at tau equal to 0. Now we are taking the sample at 30 microsecond. So this sample and this samples are very much close to each other. So the difference will be now 5 minus 4.95, and this is 0.05 volt. So this difference is even very less than the difference between the two successive samples in the case of differential pulse code modulation. So this difference is that much less that it can be represented by only one bit. The difference is that much less that you can represent this particular difference by only one bit or two levels. That is why the delta modulation is called 1 bit DPCM. That is why this delta modulation is called 1 bit DPCM, because the difference between the two samples are that much less that you can represent only by 1 bit or two levels. So it reduces the bandwidth also, because the number of bit is fixed, n is equal to 1, and the prediction and the sample difference is also very less. Bandwidth gets reduced, as I told you. N is fixed. How n can vary? N is fixed. N has been fixed to 1. And in this particular diagram, as you can see, that we are first quantizing the signal, then sampling the signal. Generally we study that first we take the sample and then quantize and then encoding, but in this particular case we are quantizing the signal, then taking the samples and then transmitting the signals by encoding, and the sampler output is taken as the feedback of the taken as input to the integrator. So here you will get the quantized signal dqt, and after sampling you will get dqk. So this dqk will go into the input of integrator, and after integrating it you will compare it with the empty. And reduce how the bandwidth will increase. Increasing the bit rate means you are increasing the bits per second. So in 1 second you can transmit more number of bits using less bandwidth. Now suppose the difference is plus delta. Okay, suppose the difference between the two signals. Okay, so try to understand this point. If the difference between the two signals is greater than 0, the output of the quantizer will be dqt is equal to plus delta. So what does it mean? When we take the difference between the two signals, we will get dt which is greater than 0. So if the dt is greater than 0, in the output you will get the plus delta. Plus delta means, I am drawing this, plus delta means you will be having the signal which is having the amplitude plus delta. Okay. Is it correct or not? Is this diagram is correct or not? Okay, yes. So if it is correct in for this particular condition, if dt is greater than 0, the output will be plus delta which will remain constant. So what you are doing is you are getting the plus delta here and now you are sampling, and we will take the sample at ts second. We will take the sample at every 30 microsecond. So this sampling interval ts is 30 microsecond for time being. We are assuming that. So after 30 microsecond what you will do? So at 0 it will reach to the delta, suppose. So at 30 microsecond what you will do? At 30 microsecond what you will do? Good evening, Shashank. Yes, what we will do? We will close the switch, and when we close the switch and instantaneously we are opening the switch, because the type of sampling we are doing is the ideal sampling or the instantaneous sampling, and in the sampling we discussed that the ideal sampling means we should get some impulse. That means we will close the switch. As we close the switch, once you close the switch you will get this sample point. This sample point you will get, and instantaneously after 30 microsecond plus 30 plus microsecond you will open the switch again. So at 30 microsecond I am closing the switch, and at 30 plus microsecond I am instantly opening the switch. So I am opening the switch after 30 microsecond, 30 plus microsecond. So at 30 microsecond, when the switch will be closed, you will get impulse of height delta. You will get impulse of height delta. So here you will get the impulse of height delta at Ts second, after Ts second, say, let us say Ts second. So whenever the input is greater than 0, input to the quantizer dt is greater than 0, whenever the input to the quantizer is greater than 0, we will get output of amplitude or strength plus delta, isn't it? So suppose after 2 Ts second, again the input to the sampling switch is plus delta. Suppose again it is coming plus delta. So when you close the switch, you will get again a impulse of magnitude delta. Now suppose the difference become negative. What will happen? Suppose the dqt will be minus delta if dt is less than 0. If dt is less than 0, the difference will be negative. Then when we switch when we close the switch at 3 Ts second, what we will get? We will get impulse of amplitude minus delta. So we will get the impulse of amplitude minus delta. Okay. So yes, Govind, correct. Negative impulse. Suppose again it is coming positive. You will get positive delta. Again it is coming negative, and you will get negative delta, and so on. So you will get only impulse of height plus delta or minus delta. Okay, so you will get the impulse of height or area plus delta or minus delta. Okay. So when you have to encode it, you will represent it by only one bit. So encoder will use one bit to represent, because bit 0 will be represented as, suppose, minus delta, and bit 1 is used to represent the plus delta. So now we can say that why we are calling it one bit quantizer, because we are having at the output of the quantizer and sampling switch plus delta or minus delta. So we are having the impulse either plus delta or minus delta. So whenever the plus delta will come, the encoder will send a bit 1. So it will transmit a bit 1, binary data 1, and whenever the minus data will come, it will transmit a bit 0. Now after getting 1 and 0, you can use any method like non-return 0, return 0, and Nyquist pulse. Whatever method you want to use for line coding you can use, but from the encoder output you will get only either 1 or 0 corresponding to plus delta and minus delta. If it is plus delta, you will transmit 1. If it is minus delta, you will transmit 0. So you are using only one bit, either 1 or 0. So that is why we are calling it as 1 bit DPCM. Is it clear to everyone? Okay. So let us draw one diagram. Watch this diagram carefully. This is a sinusoidal message signal. This is the message signal, okay? I am giving you the message signal. This is a message signal and it is sinusoidal, but it is having some amplitude at 0. So this is our message signal. The message signal empty. That means we are giving this signal empty. I have given to you, which is input to this quantizer, this summer, okay, which is input to the summer. Now, assuming that MQT is at this point, right now MCAP QT at this point at 0. Now tell me what will happen. When the message signal is greater than MCAP QT, whenever the message signal is greater than MCAP QT, dt will be greater than 0. And whenever the dt will be greater than 0, you will get the plus delta. You will have the plus delta. So we will have the plus delta here. We will have this plus delta. Okay. Now we have reached to this point at after Ts second. After Ts second, again we will compare, because after Ts second you will send the feedback signal. You will send the signal up by feedback, and that will be input to this adder, and then the message signal will come and you will take the difference again. At this point also, at Ts, this blue line is less than the black line. That means the message signal is greater than the quantized signal. So again you will get the plus delta like this. You will reach to this point, and at this point after 2 Ts second, why we are comparing every after Ts second? Because this impulses will go to the feedback path after every Ts second. So these impulses will go to this feedback path, right? So these impulses you are transmitting or giving it to the integrator. So what integrator will do? What integrator will do with the impulse? What integrator will do with the impulse? When you integrate the impulse, what you will get? Tell me what you will get. When you integrate the impulse, what you will get? A step signal. Very good, Rohan. What about others? Yes, step signal. Step signal. So this impulses we are sending to the input to the integrator, and when we integrate it, you will get the step signal of height delta. When you will integrate this impulse signal, suppose this is Ts, this is 2 Ts, this is 3 Ts, and this is 4 Ts, and when you integrate it, so because the height of the impulse is delta, when you integrate you will get step signal of height delta, and again delta, and again minus delta, and again delta, and so on. So at the integrator output we will get this signal. At the integrator output we will get this type of signal, which will have some kind of step signal. So tell me whether it is clear or not. Tell me whether it is clear or not. If you integrate this type of signal, which is having the positive and negative impulses, when you integrate the impulse, you will get the step signal which will have the height delta. which will have the height this delta, and because the step size is delta, that is why we are having that steps. Why we are drawing that steps of height delta? Because the output of the integrator is plus delta or plus delta. It depends on the difference between the two signal. If the difference is positive, you are having the plus delta. If the difference is positive, you are having the plus delta. So because of this plus delta, you are having the positive steps. You are having the positive steps. So that is why I have also applied the positive steps and positive steps. Is it okay? Now after 2 ts second, when you compare, you will find that your MQT is now greater. So whenever the MQT is greater than MT, whenever the MQT is greater than MT, the difference will be negative, and when the difference is negative, you will get negative impulse, and when you integrate the negative impulse, you will get negative step. So that is why here we will get the negative step. Again when you compare, you will get the negative impulse, again negative, and positive, 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 negative, positive, negative, and so on. So this is your quantized signal, predicted signal, or the integrator output MQT. No, there is no specific value of delta we are considering. It depends on the message signal. Okay. So tell me whether this diagram is clear or not. Tell me whether this diagram is clear or not. Okay, Nilanjana, thank you. Just I was trying to make the diagram very much clear to you. Now, as you can see that what will happen at the receiver now? What will happen at the receiver now? Okay, so this part of the transmitter is clear to everyone, I think. So how do we get the step signal? It is clear. So at the output of integrator, we will get the step signal. Now it is clear. So that step signal is actually following the message signal. That step signal is actually following the message signal. That is why at the receiver we will be able to recover our message signal with the help of integrator itself. So as I told you that in the DPCM, in the differential pulse code modulation, the receiver is nothing but the feedback path of the transmitter. So here also in the delta modulation, the receiver is nothing but feedback path of the transmitter. So what was the feedback path at the transmitter? So in the feedback path of the transmitter of the delta modulation, we were having only one thing, which is integrator. So that delta modulated signal will go into the input of the decoder, and once you pass it through the decoder, you will get the DQT. That DQT will go into the input of integrator. So this is the integrator. Now I am drawing the receiver block diagram, okay, and after the integrator, output of integrator, you will get that step signal. That step signal is nothing but because of the output of the integrator. So output of integrator is M cap QT, and this output of the integrator will go into the reconstruction filter. And this reconstruction filter, you will get the message signal. At the output of the reconstruction filter, you will get the message signal. This is block diagram of receiver. This is block diagram of receiver. Okay, so block diagram of receiver I have drawn. So here at the output of integrator, you will get the step signal. And which kind of step signal you will get? In the diagram itself, you can see what is the output of the integrator. So in the diagram, you can see the output of integrator M cap QT, which is drawn like this, which has been drawn like this. Okay, so I am drawing this. This one, what you are getting, this is what you are getting. You can see that here what you are getting. So I have drawn the output of the integrator which we are getting at the transmitter. Whatever we will get at the transmitter, we will get at the receiver, because the feedback path of the transmitter is the receiver. Actually, the feedback of the transmitter become the receiver of the delta modulation. So now when this type of signal is passed through the reconstruction filter, what output we should expect? So what you have to do is, in the step signals, connect all the peak values. So let's connect the peak value. This is the peak value, this is the peak value, peak value, peak value. Here this is the peak value, and let's connect the peak value. This reconstruction filter or the low pass filter is capable of removing the ripples or the discontinuity. So it will give us a smooth curve. When we add the peak values, whatever signal we will get, that will be the output of this reconstruction filter. So this black line will be your message signal. This black line will be your message signal, and here also you can see that what was the input of the transmitter, your message signal. Input to the transmitter is message signal, and the message signal was having the sinusoidal shape. And here also, after passing it through the reconstruction filter, we are getting the sinusoidal shape. That means we are able to recover our message signal after passing through the reconstruction filter. Anyone having any doubt? Anyone having any doubt? Yes, Rohan, clear. So everybody, yes, we are using the low pass filter. Reconstruction filter is corresponding to the low pass filter. Reconstruction name is given because it can reconstruct our message signal. It is able to reconstruct our message signal which has been sampled and which has been quantized. Okay. So I think I have explained it in detail, and now yes, so I am saying that you are not able to listen me. Okay, okay. So I was saying that tomorrow's topic will be drawback of the delta modulation and the time division multiplexing. So I think I have cleared you everything about the delta modulation and the differential pulse code modulation. What is the principle? What is the working? So we will discuss tomorrow about the drawbacks and the time division multiplexing and their questions from the delta modulation and questions from the time division multiplexing. Okay, is it clear to everyone? So can we end the session for today? Akansha, if you want to read it from the book, you can follow any textbook like Simon Hekin and like Simon Hekin, BP Lati, etc. You can follow. Thank you, Rick. Love you, dear. Shri Krishna, most welcome. All of you, most welcome. We have to make this actually number big, but we are not able to do so. Even we are discussing the most important topic of the communication system, digital communication, but many of you have gone. Yes, you can read the Sanjay Sharma also, and that is good for the Indian students, means Indian who understand the Indian language very nicely. Okay, yes, Nitish, thank you. Sanjay Sharma, you can read. There is few mistake, but that is okay if you want to read any book. That book is not a standard book, but the theoretical point has been covered. Actually, the Sanjay Sharma is copy from the different textbooks like Simon Hekin, BP Lati. He has copied everything from the different variety of textbook and have made one textbook in which all the topics are covered. Thank you, Nilanjana. That is for your compliment. Okay, so that is it for all for today. So tomorrow at 5 p.m. Yes, Taub and Schilling, you can read Taub and Schilling. You can read, that book is good, but and that is very much theoretical. There is no numerical in the solved example, but you can read the Indian authors. That's what the Indian authors is. Yes, yes, Rohan, that is correct. Taub and Schilling is good. There is a few numericals in their exercise, and the few numericals are really very good from the Taub and Schilling. So actually in the communication you have to read many books. You cannot rely on one book, you have to read many books. So that is what the students facing the problem, because by one book you will not get anything. In network theory, everybody says the Alexander Sadiku you have to follow. Okay, in EDC you have to follow the Niemann and the Streetman and SMZ. So these three books follows. If you follow these three books, you will cover each and everything, like MOS capacitor, like semiconductor physics from SMZ. So you know that from one book you can, from one or two book you can complete whole syllabus of the subjects like network, EDC and control system also. But for the especially for the communication, you cannot say any single book which covers each and everything in very good way with the good number of problems. So that is why the students face problem with the subject communication. Yes, that is Rohan is telling Akansha, you can ask Rohan, he might have preferred that book, so he will be able to tell you more about that book. What if I will say, so that will be I may be biased, because that is from the Gate Academy, that book is from the Gate Academy. You can take the feedback from others and accordingly you can purchase that book. Okay, so let's end up the session, and as I told you, tomorrow we will discuss about the time division multiplexing. Okay, thank you, love you all, good night.